Hello, Dinesh.
Hi, Leah. How are you?
Hi. Oh, wait, sorry. Can you say something once again? I hadn't sound turned off.
Oh,
Yes.
can you hear me?
Yes, I can. It was my. Okay, let's do this. At all last meeting of the semester, we're talking about BERT now, exclamation mark. And then I need to copy Zoom meeting. Yeah, I think people in general have gotten a little tired toward the end of the semester. So maybe not as much excitement. No.
I think so.
I'm personally a little like burnt out from all the classes and homeworks. Yeah. There's one more, Dinesh. Mm-hmm. How is NLP?
How is NLP? So give me a second. I'm just setting up things.
Mm-hmm.
Just give me a second.
No problem.
Yes.
Hi, Jamie.
So.
Hey there. How's everyone?
Doing okay. I assume you're also exhausted from classes and stuff. Hi, Rahul.
Yeah, definitely getting there at this point in the semester. Counting down the weeks. Not all bad, but just it's a lot of work.
Yeah.
By the way, Leah, am I audible now?
Say it again.
Am I audible?
I can hear you. Yeah.
Then I hope that everyone can. Okay.
Yeah, and I can see the screen. So. Cool.
Okay. That's cool. Let me know what we should start. I mean, I'm just waiting.
I think we can get started. I wonder, does anyone know if Van Hul Singal, did he drop the class? He kind of talked about dropping the class. I don't know. I guess he did. Yeah, I think we can go ahead.
Okay, so good morning and good evening, everyone. So today the topic of discussion is BERT, and the BERT stands for Bidirectional Encoder Representation using Transformers. So this is a model, you can say, formulated by Google, and this is like after GPT-1, I think. So this is pretty much comparing itself to GPT-1, and predecessor to it was Elmo, which I think we touched base a little bit on the last time we went through the BERT. So this time also, let's see if we can dig into it. So the basic idea of like BERT is like it's somewhat doing language understanding, as they call, because what they're trying to do is like they can now use BERT on multiple like language tasks, and hence they can claim that they have some sort of understanding about language and not just simple, you can say, fine-tuned for, let's say, one task and that's specific for that task. So that's how they're kind of saying that the BERT model understands the language. So
does
essentially,
that also
like,
mean, sorry, then I had a question. So when they say BERT also understands the language, right? Does that mean it has ability to understand common sense or extract common sense as well from the language, or it is still, let's say, semantic, a word semantic that we do, right?
so I think common sense in general that I understand is more of related to world knowledge. And I think usually if we just do language parsing and learning and training from that, usually common sense is not built that easily. So I don't think that they should be claiming that. But if you read it somewhere, then please let me know, because I don't think that BERT has claimed that common sense learning. But they have like claim that if they have been shown some sort of data, so if you can encode common sense in maybe, let's say, some textual format and then feed it into it, then I think that they should be able to get through it. But inferencing and all those stuff from text and then building world knowledge, I don't think they're claiming that. I hope that answers.
Oh, yes, as it does. This is, I was just going today with this of the class, and we came across the example of the common sense, and I have not seen anywhere mention about the common sense in any of the NLP related models, right, that we have studied so far. Most of them are until the semantic analysis, uh, and
Semantic
that's that
analysis is
was the
also semantic analysis is also like coming up. I don't think that it's to be like very well sophisticated till now also. So it's also like the BERT is, I don't think, like in the course also we have studied some semantic, but they are just using it for like starting point. Like BERT is not all in all complete package for solving semantic problems as well. So I think that this is very specific. BERT is very specific in that way. But yeah, still they talk about language understanding because they are able to perform many many tasks. So that's why. So
Thanks.
yeah. So the term here, language representation model, is basically because essentially they are finally representing the knowledge in some sort of like words are now some sort of parameters. So essentially it's represented in some other vector domain, or you can say another domain. So that's why it's a representation. So now, like coming to the main, like I talked about, is like representation from unlabeled text by jointly conditioning on both left and right. So BERT is using contextual embeddings, and what it means is like it will see both the left and the right context, and then it will produce the representation for the word. It's not like you can say RNNs which are going to look only towards left, and bidirectional RNNs which do shallow concatenation. And if you do like encoder, transformer decoder, so that's a term used here, which means like we only look towards the left, like we do in decoder side of the transformer. So that is like also unidirectional. So BERT uses both directions. We'll see the architecture in some moment, so bear with me. So now we'll talk about fine-tuning and feature-based learning. So they mention about them, and I just got to know from this paper about these two paradigms. So I think this would help. We'll go over that in introduction. So these are some of the results. They claim that they have, improved many of the state-of-the-art tasks and all those stuff. They have not mentioned here one very important test that I saw in another research paper based on BERT, which is, improving BERT. I think that's excellent. But that was like earlier it was performing 44%, but with BERT they were now performing, I think, 80%. So like 100% improvement. So that was really crazy. So that data set was race. So it's something related to multilingual languages and Chinese and English. So you can have a look over that in your free time. Okay, so coming to the introduction. So it talks about pre-training as a method for basically solving some of the language tasks. So essentially pre-training means like some sort of, you can say, transfer learning, and we can pre-train the architecture on some, maybe let's say, smaller data set, and then finally you can take the whole architecture and then fine tune it to your domain. So that sort of transfer learning. And this has been studied according to the paper in many like research papers. So I'll just go over that quickly. So it's in NLI, which is natural language inference and paraphrasing, and many token level tasks such as name entity recognition and question answering. So all these tasks are helped by, pre-training as a technique. So you can like pre-train at sentence level, or you can pre-train at token level. So that's what they were doing. They were mentioning in the previous paragraph. So now coming back to these two techniques. So feature-based and fine-tuning. So what happened is like in feature-based learning, what you can think of like is in Elmo, they have mentioned it's a feature-based. And what happened is like you have some sort of word embeddings that you get, and then you directly use those word embeddings. You don't bring the whole architecture, you bring the features from that previous architectures. You can think like that. And in fine tuning, you bring the whole architecture all together and you fine tune the architecture parameters rather than the downstream parameters. You fine tune the whole parameter that was in the earlier base, you can say, model. And over top, you have some layers, then yeah, definitely you would be fine tuning them as well. So in Elmo, I'll just touch base on it quickly. Elmo is basically simply bidirectional RNNs with the feature output as, concatenation of the left and right side for each word. So let's say if you have a word, today is Sunday. So for is, we can have like left context and right context. We just concatenate it for is, then for each, like. So yeah, this is for Elmo. Now they have like I was talking about fine tuning approach. So GPT uses fine tuning as well, but the only problem with GPT was that GPT used only unidirectional and not bidirectional encoding. So what happened is that they like build up on that and they release BERT. So you can think BERT as a successor of GPT. So they have mentioned here that you take up all the parameters and you fine tune all the parameters, pre-trained parameters, and that's the fine tuning approach. So that was about fine tuning approach. Okay. This is important, I would say. Like the objective for both feature-based and fine-tuning are same. It's just that the downstream tasks consume the models in a different way. So they were trained on the same objective function, and it's just that the methodology of training was different. Parameters initialization that were different, but yeah, the objective was same, like maybe language modeling and, or you can say question answering or next sentence prediction like BERT does. So the objectives are same, but the way are different. Okay, so now this is what they are proposing that. So the limitation is that standard language models are unidirectional. So this is pretty old model. So maybe if you're thinking like why it's such a big thing for having bidirectional, like I was a little bit shocked like how this can be so famous, this so simple technique, but this pretty old model, and I think we are in 3-4 years ahead, so that's why it might look like why it's a big deal of having bidirectional as a big gain up. So yeah, and now they have shown that it does in this paper, and they talk about GPT again, like so what they're talking about here is that restriction applied by the GPT. So like the left to right is one thing that they applied, and they say that such restrictions are very suboptimal for sentence level tasks and could be very harmful. So like they're saying that context where context is required, definitely unidirectional is going to be suboptimal. So I think this is not new for us. So I'll just quickly skim through this. Now, what they have objective is the mask language model. So they change their like objective function for like their own preference, and they call it masked language model, which is based on the closed task. So I think you all must be aware about it. Closed task is like fill in the blanks. We have a sentence and we have blanks in which we just fill the words which you think it's the the right word. So that's what MLM is like, and they just rename it. I don't know why. Maybe they want it to be cool. So okay, so they mention here that like I just mentioned that objective function of MLM, and they take both left to right context with just masking done. So, and the other thing is that next sentence prediction. So we'll come to this next sentence prediction in more depth a little later. I think they have not mentioned it here. They just introduce it. So they just mentioned that text pair representation is also learned. So what happened is like we have a sequence which is fed in, which is actually a pair of sentences, and those representations are also learned via the BERT model. We'll come that in more detail. So this is like what they are what their contribution after this paper would be. This would be the brief of it. So they just showed the importance of bidirectional pre-training, which was not in GPT-1, and so Peters et al. Is basically Elmo. So they use shallow concatenation of left to right and right to left. So in Elmo feature-based learning, we just do concatenation, though that is not termed as deeply bidirectional. So deeply bidirectional is like one of the new terms that I learned here. So like deeply bidirectional means like you can be sure about like the context is with everyone. Whereas in left to right and right to left, usually what happens is like even if you apply LSTMs, there are chances that context is going to be messed up, basically because of multiple application of um, ReLU or whatever gates and all those. Now they have also contributed in the way like pre-trained representation reduce the need for heavily engineered specific architecture. Yes, so this is like the output. Like now you don't need any task specific architecture downstream. You just use BERT, and over the top of it, you just apply your own output layers, and you're done. So those output layers are just simply feed forward networks. So you don't need much to do. Now, so unsupervised feature-based approaches. So this is talking about representation of words like word to vec and all those. So we all know that this is pretty important thing. They just mentioned it. It's important, you know. What they now talk about is like word embeddings learning have been generalized to coarser granularity. So like now they're more models which are, you know, representing sentences, paragraphs, like sentence embeddings in Kiros, paragraph embeddings in this research paper. So they're saying that it over the time got coarser and coarser representation. So what was the objective to do that? So they have mentioned that. So they wanted to rank the next sentence. So maybe you can provide uh, this architecture in NLI, like, or maybe entailment. So if you provide two sentences, whether these two are like next sentence or not. So that's why such coarser representation were invented. And now they have also mentioned like denoising autoencoder objectives and all those things too. You know, some of the other objectives for coarser granularity. So again, these autoencoders are again generative. So if we have sentence level representation, then maybe we can generate better sentences. So, I mean, we use the previous sentence representation, and that's how we can generate better sentences. Now coming to Elmo and its predecessor. What they're trying to say is like they extract context sensitive features that we know. So basically Elmo is, like I told you, is basically simply bidirectional LSTM. So it is trying to extract some context sensitive features. So I'll skip this part. Now they have mentioned some of the research papers. So they propose contextual representation. This is interesting. So some of the research papers have not just simply done language modeling, they are trying to guess a single word from both left and right context to build up the context representation and extract context features. So there are some papers like this one, Mahmood et al., which is trying to, you know, guess a word in the left context and in the right context of the token that we are looking at. So that's how they are trying to build the contextual representation. But again, they have mentioned that these are not deeply bidirectional, and there are some research papers that say that closed tasks can be used to improve text generation on such models. So again, coming to the point, like they are not deeply bidirectional. So fine-tuning approaches which are unsupervised. So the thing with feature-based approaches, like they carry the like the idea from the feature that the first works in these directions, only pre-trained word embedding. So unsupervised fine-tuning, like the BERT is doing right now, unsupervised and self-supervised, earlier in this direction were like borrowed from the feature-based approaches. That's what they're trying to say. I've not gone through these research papers still, so maybe I could have briefed, but let's skip them. So Now they're talking about document encoders, sentence or document encoders, which produce contextual token representation that have been pre-trained from unlabeled text and fine-tuned for a supervised downstream task. So these are sentence level or document level encoders that have been trained on like unlabeled text, and they are like fine-tuned on downstream tasks, but they are again not, what the BERT is trying to do. So they are trying to say that sentence and document level encoders have been there, but not the word level that they are trying to do, and not even the way they have done, like transformer, using transformer. So they mentioned about their advantages, like no need for learning all the parameters again, and OpenAI GPT attained using these unsupervised fine-tuning approach, state of the art. So they just mention about previous work.
Can you please share some example of this particular thing? Can you please go back? So when they say unsupervised fine-tuning based approach, let's say our task is next sentence prediction, right?
Yeah. We would be going over that. This is just introduction. So if you want to go over that right now, like we can, but I mean, it would be best if we have flow in the.
Sure,
Yeah.
sure. Okay, yeah.
So this is one of the tasks that is being performed by BERT. So we would be going over that. So that's not. Let's not look ahead. We'll be there. So now they have transfer learning from supervised data. So I think that majorly they have shown some of the papers which are able to do this natural language inferences. So inferences would be like done on supervised data. If someone is training on inference data, so it would be labeled. So that's why they have shown NLI example and machine translation and transfer learning. Using that, they are saying that it's showing effective transfer from supervised tasks. So I've not gone much detail, but yeah, this is not what they're trying to do. They are doing self-supervised. They don't have supervised data. I just think that they mentioned for completeness. So now coming to BERT. So BERT is just like unsupervised fine-tuning model, like they had mentioned before. So they have two steps in that. The first is pre-training and then fine-tuning. So pre-training is a stage where you generate a, let's say, generic model, and then fine-tuning is like for a task, you just fine-tune that generic model. So they mentioned that during pre-training, the model is trained on unlabeled data over different pre-training tasks. So the different pre-training tasks that they have defined are basically should be applicable to unlabeled data, and they are the next sentence prediction and masked language modeling, MLM. We'll go over that also. So now for fine-tuning is initialized with the pre-trained parameters that are learned during the pre-training, and all of the parameters are then fine-tuned according to the label data. Now we are incorporating the label data because downstream tasks, specific tasks would be having some label data. So now they'll have some label data. So this is the basically distinctive feature that they talk about is like unified architecture, definitely. Now the model architecture. So model architecture is pretty simple. They have not even gone in depth because it carries mostly from the transformers. And just to briefly mention, this is how it looks, the left side where my cursor is. So as you can see, the input sequence, then this BERT. So they have stacking of transformer blocks. They are bidirectional. They are, like, as you can see, crossing to all other transformers, and then they produce the representation. So now after these parameters are learned, they are now they are employed, sorry, in different downstream tasks like squad, MNLI, NER, name entity recognition, all those. So they have two configuration that they usually compare. It's BERT base and BERT large. So they have 12 layers of transformer blocks. Hidden representation is 768 and 12 multi-heads in base. BERT large, they have 24 layers, 1024 hidden dimension. Yeah, so the parameters are almost thrice. And I think there is one more BERT XL, which has, I think, almost close to billion. So they have not mentioned it. It's in other, I think, research papers. Yeah. So now they are mentioning that again, like transformers use like bidirectional, whereas GPT use self-attention constraint to only context to its left. So this type of attention they have called as a decoder attention, and the one that is being used about, they call it encoder attention. So that was from the model perspective. Like, anybody has any doubt on model architecture? Pretty simple, I think. Okay, so now they talk about the input and the output representation. This is interesting. I learned word piece, new thing here. So what is they're doing is like they are pre-trained on two tasks. The one is basically MLM, and the other is sentence pair, next sentence prediction. So in next sentence prediction, they need two sentences concatenated. So what they do is, like, as you can see here, they have this separator. This separator tells that the text ahead of the separator is the sentence B, and the text before it is sentence A. So that's how they are separating that. After that, they have word piece embeddings that they are using for representing tokens. And then they are using two more embeddings, which is positional embeddings and segment embeddings. So I'll just quickly move to that image. So as you can see here, token embeddings would be the word piece embeddings, or maybe like if you want to create your own BERT architecture, you can use any other. They are using word piece. Now they are having segment embeddings. So like these are all the A sentence and these are all the B sentence words. So they will be having EB and they will be having EA. Then they have positional embeddings, which is like what's the position in the sequence. So these are all positional and segment embeddings, I think cosine functions like we had studied in transformers. So just to have some correlation between different words. Now output representation. And yeah, one CLS token is also passed. That's for next sentence prediction. So as you can see here, this CLS token is always in the beginning. So basically it just, so basically the transformer blocks just above the CLS are going to look at all the right-hand side of the CLS token. So it's something classification. So basically they are going to look all the sentences, words, sorry, and in a sequential manner. So they are going to classify whether it's the next sentence or not. So they are using that output C as a next sentence prediction binary classifier. So if it's one, it's a next sentence. If it's not, then it's not. Then it's not a next sentence. That's about the input and output representation. So now, task one, which is
please go back to that image on the architecture image. So the question I had, let's say we are talking about the NSP, right? The during the pre-training phase, this is the one network, right, which is trained upfront, and it has its own objective function, maybe unsupervised learning task. Is it correct interpretation?
Sorry, can you go again? I think I didn't understand that.
So this the pre-training is one network, right? And
Yes.
it has different objective function for different tasks. Is it correct, or the entire network has a common objective function irrespective of the task? Once this entire pre-training network is trained, then once the parameters are learned, then they have the feed forward network or maybe some additional layers on top of that, specific to the task, like a squared NER.
So
Is it
basically you
correct?
can think like, these two objective function are tested together only, and they are not like in one step. So like what happened is like, let's take this question and like after discussing the two, maybe, what do you say? Because I would be discussing about the masked LM and NSP. So keep these two questions on hold, like just
Okay.
for 2 minutes. Just 2 minutes, because once maybe that solves your problem also. So masked LM is one of the tasks that BERT is being trained on. So masking is important in bidirectional. That is intuitive, because if you don't have masking, then maybe some top layers can easily detect that the word that was required, and then context is then passed on to the word that was to be required, and somehow cheating can be done in some way, like the word that needs to be guessed somehow knows like what word is there. So like I don't have a sketch pad here, but I think it's pretty intuitive. Like the embeddings of the word that is to be guessed would be in the context of some other, let's say, hidden state, and that hidden state would be used in, let's say, a top layer or maybe higher layers. So it's going to be somehow cheat and just easily give up the embeddings that were to be guessed. So they just masked it, and after they just after masking, what they do is like only the words that are masked, they just take the output of that, and then they do cross entropy loss. So to talk about that here a little bit, that
so
it's related to closed task and all those.
Can I?
Yeah, sure.
So I understand this,
Sure.
this idea. This makes a lot of sense, that if you have bidirectional encodings, then the word will be able to predict itself based on the neighbor's context, which, internal.
Contains that.
But then I kind of missed what the takeaway is. So how do we fight that? What's our approach instead?
Okay, so our approach is we simply mask it. So like, I think we have done that masking in transformers in decoder side, where we mask the right-hand side of the word that we are guessing. It's something similar to that. You can think it like that. In that way, even if we do complete computation with having minus infinities, we won't be able to incorporate those values. So something of that sort.
Oh, okay.
Or you can simply have, zeros. Anyway, like it's your wish. Or you can have mask token, which has I'm not sure about this. Anyone can correct me, but till now what I have understood is like mask token can be represented in some embedding in form of embeddings, which will maybe, let's say, have 000 zeros or some sort. So that's how we can do. I hope that clears.
But mask also, they have given a different approach, right? Let's say you have a mask token, 10% or 15% of the time they generated with the random word, right?
Sure.
Yeah.
Yeah. I'll just go over that. So what's the intuition behind that? I'll also discuss that. So this is just mentioning that it's actually called closed tasks. And so basically they're saying that they don't mask like all the words. Definitely they masked only few words, like it's in closed tasks. So it's mentioned that only 15% of all word piece token in each sequence at random. So if you have, let's say, today is last day of month, then last or maybe month would be like 15% of this whole sequence, and just mask them, the number of words that comes out. But there's some issue with that. So if we do that for MLM, that is fine, but downstream tasks like NLI and all those like are going to be affected. So it's mentioned here that we are actually creating a mismatch between pre-training and fine-tuning. So pre-training are having now mask tokens, whereas in the case of fine-tuning, when we are doing on, let's say, text pair, we are not going to, have missing words or mask tokens in them. So that's a mismatch we are going to produce. So what they do is like they only replace 80% of the 15% with the mask tokens, and with the random tokens 10%, and they don't change for the 10% of the time. So they have done some experimentation. It's mentioned in C.2 appendix. I've seen some experiments and they are pretty random. I don't think that they have any intuition for why it's working off 80% and not for, let's say, 70% or so. So they have just done some random experiments and they've come to know that 80% works. So that's the idea. Like, so just one more intuition I can share is like, let's say if you have multiple mask tokens, so essentially what you're doing is like, if you're blindly just masking and not doing some only like percentage of it, so what essentially you're doing is like you're removing information from the context. So if multiple mask tokens appear together, so the first mask token will have was expecting, let's say, today is the last month of the day. Sorry, today is the last day of the month, and let's say day is mask. So day mask was expecting all other words. Similarly, if we had month also masked, then month was expecting day also in its context, but now both of them are masked. So that's the issue, right? So they don't want to blindly mask. They just want only 15%, 80%, like the 15% of sentence word piece, and out of that 80% only, so that there are some sort of um, like downstream and as well as some sort of contextual information also there for other mask tokens. So that's covered in, I think, ExcelNet. So I think there are a lot of problems in BERT. People just keep on publishing paper. I think over the years on improving BERT, there are a lot of paper now. So yeah. Now coming to next sentence prediction. So next sentence prediction is pretty simple. It's just that how they are producing the data is something I think maybe you guys can use in future, how self-supervised things are done. So it's just like 50% of the time they are just taking up two sentences which are actually like adjacent, and 50% of time which are not adjacent. So they just smartly created that data from unlabeled data, and then they just passed on to the BERT, and they just used the C output, that was the classifier output, for knowing whether it's next sentence or not. So in some papers they have mentioned like this conflates the coherence with uh, sentence ordering. So like like to give an idea, there can be two sentences which are next to one another, but they are not that coherent. So to like fine grain identify whether things are coherent or not, and then guess whether it's next sentence or not, is some other are trying in some papers, and here they are just trying whether it's next sentence or not. So I think we have gone over in last week 12 and 11 about coherence recurrence, so you guys can relate, like it's like that. So if there is some sort of inference or rhetoric structure, then there is going to be coherence. But if it's there is, let's say, global argument, like on maybe first sentence is on one claim and the other is for global argument for like in an against, so those two might not look like next sentences. So that's why coherence is important. So they have mentioned in other paper like that. So
I lost. I can't see your screen anymore. Okay, I can see it again. Dinesh, you're muted in both of your windows, just FYI.
oh, sorry.
Yeah, okay.
So yeah, so where till where did you hear me?
Yeah,
like
okay.
Before I dropped off.
Oh, where
Yeah,
I think this was the place. I kind of
like
you were talking about how a counter argument wouldn't look like the sentence. Does that make sense?
mm-hmm. Yeah, so I think that was what I was talking about in the last. So if anybody, like Rahul, you had few questions, so maybe you can go ahead now.
Yes, my question was on this objective function for each of the pre-training tasks, right? So let's say the task is language modeling, and we are trying to train the model on pre-training phase. In that case, um, the pre-training network objective would be to guess the mask token, right? And
And
train the
the
entire
next sentence prediction also. They are pre-trained
together.
on two objectives. Yeah, you can like simply say um, like what happened is like you can just take the masked LM outputs to one, you can say, feed forward, and C output is simply like binary classifier output. So I don't think that we would need uh, any feed forward network in front of that. So if we just use even if we like, we can definitely, so we can have feed forward for that, and then we can just flow back the errors, cross entropy errors parallelly, both for both. I hope that answers.
Okay. Yeah, this answers certainly. Let's say we talk about the fine-tuning phase. Let's say I have my own task uh, wherein I'm trying to do some named entity recognition, for an example, right? So in that case, I would have my on the feed forward layer, maybe one or two layers I will add on top of the uh, pre-training the learned parameters, and then try to train the whole network. Is that the right understanding? Or once the pre-training is done, how exactly the architecture look like, let's say for any
Hello.
task? Yes, Dennis, we can hear you.
I think my net is pretty slow today. Just give me a second. I'll change my net. Yeah. Hello.
We can hear you. Mhm.
Yeah. So you were saying about name entity recognition, Rahul. Yeah, you can go ahead.
Yes. So once we have our pre-training, the parameters learned, right? Then next,
Mm-hmm.
on the fine-tuning phase, let's say our task is NER, and we
Mm-hmm.
add, let's say, one linear layer, and then we have our final, the objective on which we are trying to
Yeah.
calculate this. So
Mm-hmm.
is that the correct understanding? That's how we built the whole network for the fine-tuning?
Yeah. Yeah. So basically, for fine tuning, you remove the top layer that was in the BERT. I mean, I'm telling you, um, from the perspective of this paper, implementation wise, maybe there are modules which directly supplies removed top layer, in which top layer are removed. So talking about the left structure, you can see here, we can say like we remove the top layer that was used by BERT for language modeling and NSP. We attach our own top layers to that, which takes in the input of the like these tokens. So this T is actually the output representations. So whichever we want to use, we can just use that. And like, so if your name entity recognition is like going to so the tokens are going to be some, let's say, vectors, and if they output some named entity when you do like feed forward and then you do softmax over the vocabulary, then like that would be your training the feed forward. You would be applying that feed forward and removing the language modeling. Does that answer?
Yes. Uh, yes, it does. And
Sure,
then
sure.
in fine-tuning approach, we do not have anything bidirectional or anything, right? If we look at this image, it is in fine-tuning, we have just a normal, fully connected layer, or then, right?
Yeah,
Is
like
that what we do?
it's like it's up to you. So basically, these output representation are just the representation of the tokens that were fed in, and they're like pre-trained on like language modeling and next sentence prediction. So ideally it should be somewhat related to that task should be, but they are somehow empirically performing good on other as well. So if you try to have another top of that, another, let's say, transformer layer, multi-headed attention and all those, you can have that. These are just representations. So you can think of BERT like you're not using word to vec anymore. Word to vec embeddings. You're using BERT embeddings. You can think of like that. There's nothing else. Over top of that, you want to build anything you want to, you can build that.
Okay. Thanks. And I was just trying simple one example using Hugging Face. That library is there, right? And that
Right,
hides
right.
entire complexity of it. I was not getting what's happening behind the scene, though I was looking at the implementation that also is quite complex. Maybe I have to learn more about the transformers and these networks, then we'll be able to understand. So I was not able to understand the whole picture behind the scene, though I was able to get my expected results. I, to some extent, I was getting good results.
So I think after maybe today you'll have some more, let's say, understanding. There are some gaps. I don't think that even I understand it correctly because BERT in itself is pretty huge. So yeah, in the interest of time, we'll just quickly move ahead now. So uh, input output representation is done. So next sentence prediction is done. So there are some papers mentioned which have done these objectives. So basically, they just mentioned that even if the objectives were same, they used to transfer the sentence embeddings, but the BERT is transfer whole architecture. So transfer learning is happening. Now they are told that they are going to use book corpus and English Wikipedia, and that is because they don't want a shuffled sentence level corpus. So because like if you have shuffled words, then you won't be able to predict next sentence for sure. So now talking about fine tuning. So fine tuning is like how what they have mentioned in this paragraph is pretty beautiful. I would say they've just said that whatever task you give, it can be mapped to the task that they have pre-trained on. So like they say that at the input sentence A and B from pre-training are analogous to. So they are saying that what are all the tasks that can be like used for and how they are analogous. So sentence pair paraphrasing. So if you have sentence pair which are paraphrased, you're still gonna realize whether they're next sentence or not. Hypothesis, premise, pairs, entailment. So if you have hypothesis and premise, you're gonna say these are entailments or not. Question passage pairs in question answering, you're gonna like squad. So you're gonna easily generate the answer from that. So and the one that you were talking about, Rahul, is degenerate text file text classification or sequence tagging. So NER can be thought of as sequence tagging. So in that case, you'll have phi in the pair, and then you can use this like output token representation are fed into output layer. So this output layer can be your layer, and then for token level tasks such as sequence tagging, question answering, is fed into output layer for classification such as, so these are token level tasks. So for that you can have an output layer. Similarly, you can have for other like classification also, they have mentioned that you can have an output layer for classification. So that was about the architecture, and I won't go into the experiments. They are pretty interesting, and like I would suggest to have a look over it. Like squad is like they provide the question and the Wikipedia passage, then the task is to predict the next answer text span in the passage, predict the answer text span in the passage. So they like do it by the start and the end, and start and the end can be like done via token level tasks mentioned here. So pretty interesting. There are many improvements. I'll just quickly mention that. So many papers have improved over BERT. So ExcelNet, Roberta, or Albert, and all those have improved BERT. So you guys can also have a look over that. And that's it from my side. On time, I guess. Anybody has any questions?
I don't have any questions, but this definitely helped me understand it more.
Sure.
One question I had, which I came across when I was going over some of the things, and that says BERT does not achieve really, that good performance on long sentences. And I was not able to correlate things. If you have some insights, why uh, long sentences would be a concern in case of BERT.
Yeah, so I think long sentences for like any transformer base is going to be concerned. So there is one transformer Excel architecture which handles this, and they don't use that. So transformer Excel does like, it's pretty interesting. What they do is like they share the contextual representation in the to the like forward spans, you can say. So what happens is like we have uh, some amount of sequence length, and if we go beyond that, then we have to do some sort of, maybe you can say, chopping. So that's why. But what happens in Transformer XL is that even if you do that chopping, you are somehow able to preserve the context. So that is the idea. I can just quickly open that paper. That is for like big length,
Okay.
like moving beyond fixed length context. So that is the idea. I think you can see like in any like very long text sentences, any transformer model is going to be like, according to this paper, you can read this paper only and you can see like they mention this only. So
Got it.
any other question, guys? Ilya,
No,
do you have any questions?
no. Thanks for presenting. Or no more a complete mistake in it. Yeah, Jamie.
Just one thing I
Thank you, Ken.
That's one thing I wanted to call out. I'm not sure if we would have more sessions. If this is the last, I just wanted to say, Dinesh, I always enjoyed your sessions, even other sessions as well. But yours were always, very informative and thorough. You have done really excellent homework. I think the way you approach and explain, uh, really,
Thanks.
I appreciate that. Thank you.
Thanks, Rahul.
Yeah,
Thanks. That means a lot.
good stuff.
Yeah.
Cool. Right.
Cool.
See you guys next semester. I'll post a little poll asking people if these meetings help them at all in Slack.
So
Yeah.
just one thing, Ilya, I wanted to mention, like once we are done with this course, like just maybe we guys can sync up for like 1 hour meeting, like maybe some sort of chillaxing way, like not for reading research papers, maybe.
Yeah. Done for that. We've already had one, and I think another one. Sure. That sounds like a good idea to me.
Sure.
Cool.
Thank you, guys. Thank you for your time.
All right. Good night. Bye.
Bye. Bye, guys.